Hi, everybody. Sorry about that. We had a little bit of technical difficulty. Every time we think we have Zoom and Facebook figured out and take it for granted, they like to change things on us, and it tonight was giving us some problems. So thank you for joining us. Just a few notes on our calendar for February. On the 5th, which is this Saturday, it's a public night at our observatory at 7:30. The 15th is our astronomy fundamentals at 7 p.m. That'll be streaming here on Facebook, and that'll be an introduction to the EV scope. February 19th is a public night at our observatory at 7:30, and February 26th is a members only night at our observatory. I don't think I'm sharing my screen, am I? Sorry about that. If you have questions tonight, you can comment on the Facebook post on this video post, or you can email questions@naperastro.org, and Chris will try to feed those questions to our speaker, Jim, tonight. So tonight our speaker is Jim Annis. The title of his topic is Cosmology is Gravity. And Jim got his PhD from the University of Hawaii, which meant he got to spend a lot of time on Mauna Kea. And now he works for Fermilab, and he works at the Rubin Observatory, LSST. So Jim, if you're ready, I'm going to turn things over to you.
Well, I'm ready. And it looks like you're seeing me.
Yes.
So I'm going to spend tonight talking about physical cosmology, about gravity and matter and the cosmic microwave background. I have my own obsessions, which I'm going to share with you tonight. You might see some of them in the background, my library. I spend a lot of time in books. So a lot of what I see tonight is thought and not so much experiment, but we'll see. I don't really ever know if I want to talk about the stars, the planets, or rocks. So what you're seeing on the right is Blanco telescope, really the mountaintop called Cerro Tololo. And I spent a lot of time there last decade. And this is the walk from the dormitory up to the telescopes. And I love this walk. It makes me feel like I'm a real astronomer. Whereas the spinning stars, I get to see that in the middle of the night, but I don't really want to be walking on the mountaintop when I'm doing that. It's spectacular in the dark, but it is in the dark. But when you're walking up to a telescope, you can grab rocks that you can bring home with you. I have in my hand, you can't see, a piece of andesite that is right there from that road. I still have it after 5-6 years because it reminds me of being at mountaintop and looking at the stars. And soon enough, oh, we're almost there. It's about a 20-minute walk. Soon enough, you'll see the Blanco telescope. There's a lot of telescopes at CTIO. Most of them about 1 meter. The Blanco is about a 4-meter telescope. There we go, the silver dome one. But one of the things I had to figure out is how to talk to you about cosmology. What about how are we going to approach talking about cosmology? And I'm a book hound, so I go back to old books like Aristotle, because remarkably enough, you see things in Aristotle that shouldn't be there. Like the most exact of the sciences are those that deal most directly with first principles. Or for we think we know a thing when we know its first principles, its origins, and its elements. And those things sound modern to my ear. They're written 330 BC. Aristotle is displaying his obsession with a word called arche, which here is translated as first principle. It kind of means commanding origin or first things. So when he says he wants to know its first things, he wants to know its first principles, origins, and elements. They've all come over the millennia to mean particular things.
Jim, excuse me. If
Yes.
if you're showing a slide, we're not seeing it. We're seeing you. I just wanted to make sure.
Sorry. Thank you so much.
Yeah.
My technical setup, like yours, is a bit complicated, and sometimes it doesn't work like I expect it to. first principles. So when I was being taught, when I was a young student in college, we were told things like, well, to really know something, you have to derive it from first principles. You must just write down Newton's second law or Newton's law of gravitation. And that's deriving from first principles. That doesn't have meaning. They never used Aristotle. They never told us Aristotle, but it comes from Aristotle. It's a palimpsest, something that is lost its original covering, yet underneath you can see where it came from. But these first principles ideas are rampant. Like, let's imagine that on September 14th, 2021, I was on a pull-up bar 2 meters above the ground. And if I fell, how long would I have to contemplate my oncoming hip fracture? Well, I can do that from first principles. One writes down F equals ma, one writes down the differential equation, one integrates twice, one finds out distance is equal to 1/2 at squared, solve for t. Do that. I know acceleration is 9.8 meters per second, so 600 milliseconds of time to think about the ground coming at me. Pure Newton's physics from first principles. And I'm recovering nicely, thank you. I can walk without a cane currently. If I think about it, I don't even limp. But this idea of first principles is important in cosmology because we usually do scaling laws. Recently, LIGO has been discovering binary black hole mergers. And remarkably, they measure a direct first principles distance to a binary black hole merger because it's a super simple system. Instead of the Earth being assumed to be a point source as I fell to its surface, they assume both black holes are point sources and orbit around each other. And then the resulting strain, which is stretching, is just a phase. Cosine theta has to do with the orbits of two black holes around each other. A mass, which sets the amplitude, and a distance, which tries to decrement the amplitude of the strain. But the mass, a chirp mass, you can actually get from the way the frequency decays. It's F dot over F. You don't derive chirp mass from first principles, I do not believe, but you do get this equation for strain, and you get a distance out of it. First principles distance. So I'm going to show you a few artifacts tonight. Here's the first one, LIGO, and at Hanford on the left, at Livingston, Louisiana on the top, and Virgo near Pisa in Italy. These are laser interferometer gravitational wave observatories. They're laser measuring sticks, and a strain is delta H, delta length over length, and they can measure very precise strains. And they measure the strains of gravitational waves from binary black holes merging. Another thing that Aristotle said was, if we look to ancient thinkers, natural science would seem to be concerned with matter alone. So that's great. Physicists today usually just think about matter, but they also think about gravity. But what he was doing was complaining about the Ionians from 300 years before, who, instead of invoking gods and souls and the like, just tried to explain nature with nature. Aristotle didn't actually agree with that. On the other hand, the Ionian worldview is that we can understand if we think deeply about something and we read about what other people thought deeply about it, we can make progress. So Aristotle's 3 books, he wrote a lot of books, most of them are not very interesting to me, but 3 are Physics, where he went through this idea of motion being intimately related to the thing, the element. One element had one kind of motion, another element had a different kind of motion. His Metaphysics, where he talked about matter and elements, and Dikailo, or On the World, where he talked about the sky and the world underneath it, everything underneath it. And especially Metaphysics left a palimpsest on physics, mostly through medieval times, where he was studied a lot. But you'll see, he studied motion and matter and elements and the world. And today we study things that remarkably look very similar. Physical cosmology today is the standard model of physics and general relativity. On the left is the standard model of physics. In the blue are the constituents of protons and neutrons called the quarks. They're mostly what we think of as normal matter. In the lower left are the three things that seem like electrons, electron, the muon, and tau. Muon and tau, for all the world, are just like heavy electrons. They differ practically not a bit by electrons other than their mass. On the lower right are the neutrinos, which have something to do with electrons and muons and taus, but they barely exist. They just carry a few quantum numbers, and they change flavors at will, and they change masses at will. In the middle are the four force bosons, the photon for electromagnetism, the W and Z bosons carry electroweak force, and the gluon which carries the strong force. And in the middle is the Higgs boson, which carries the mass. It gives other elements their mass, and it gives them, it provides the capping stone to the standard model of physics. That standard model of physics is what we mean by matter. Notice that radiation is in there in photons, or radiation as we think of radioactive materials is in there as a W boson. Gravity is not in that. It stands at the outside. Gravity is general relativity these days. It's well, that equation at the top is Einstein's field equation. And it says that gravity is space-time curvature. Matter tells space-time what shape to have, and space-time tells matter how to free fall. So cosmology is a shape of space-time and its matter content. So we're all familiar with gravity wells, like it's in science fiction if nothing else, but we always talk about them. And massive dense things make gravity wells. So the star, say the sun, is telling gravity how to shape space-time around the star. The matter content, the universe tells the universe what its space-time shape should be. And the space-time shape of the universe tells matter how to flow, how to move. We'll come back to that quite a bit. So gravity is a simple idea. Even general relativity is simple compared to the standard model, but it's not intuitive. And I'll give you an idea of what I mean by not being intuitive. Curved space-time has funny features. This is not curved space-time, but these actors are moving in non-Newtonian ways. And it takes a while for the brain to figure out what's going on. And I love it because it looks like they're falling, but they're falling in a funny curved way because the slide is telling them how to fall. If you think of the slide as gravity, you're exactly in the right place. Except that they're so lightweight, they do not tell gravity how to be shaped. What Aristotle really liked was Plato's stuff. So Plato was earlier than Aristotle, 30 years. He wrote this book called Timaeus, and it is deeply weird. It's also very deeply influential. What I can say about deeply weird is you can read this list of things that he thinks is part of his cosmology. There's one sky, it's a living creature with intelligence, a soul, and a body. Its shape is the perfect shape, a sphere. There's only one soul world from Earth to sky. Motion pre-exists. One rotation of the sky is pure, because spheres have slows, and the spheres slide. The spheres being planets and stars and the sun and the moon. Time exists because of the star soul's motion. Souls are assigned to both humans and to stars. The perfect rational is real, but the necessity is matter. The messy necessity becomes matter. Matter's all around us. It doesn't work well, but the rational shines through. Matter is earth, water, air, and fire combined in the planetonic solids, and the motions of the soul spheres are harmonic ratios. It's deeply strange and deeply influential. I can give you another idea of what I mean by that. This is my second artifact. It's a book in the Vatican Library. It's from the 1300s. It's Timaeus by Plato in the center. Around the outskirts is the Chalcidius's commentary. And the commentary is trying to explain what Plato's talking about, Timaeus. And you'll see that on the left, Chalcidius has lots of things to say about what Plato is saying, in between the lines, outside the lines. And then he stops. He hit a place where Plato was particularly obscure, I think. That's just the nature of that book. So how does something like this, written in Athens in 360, ever become influential? Well, essentially because of inflation. Not what we mean by inflation, but as cosmologists, but something very akin to it. Alexander the Great, right after Plato was flourishing, took over the Persian Empire and spread Greeks as kings and emperors all over the Eastern Mediterranean. And 100 years later, those Greeks are trying to figure out what it meant to be Greek. So they reached back to Athens, the glory days of Athens, and tried to think being Greek meant thinking like Athenians. And Plato was the archetype Athenian. So reaching back to Plato was reaching back to being Greek. And Plato moved over the Eastern Mediterranean. And when the Romans started taking over the Western and Eastern Mediterranean, they looked at the Greeks, thought they must be civilized, and took it on. So when Chalcidius was writing in 360 AD, it was only natural that he was looking at this book that spread by conquest, but then by influence over the whole Mediterranean. Inflation. So Plato was drunk on rotation. He's drunk on the circular motions of stars, that are eternal and perfect. And his whole cosmology is based on this. I mean, you can understand that, especially if you don't have TV sets and you're sitting out at night watching the stars move. But it's strange by our standards because we know the Earth is rotating. It's not the stars that are moving, the Earth is spinning underneath the stars. And yet that palimpsest lives on in us, this obsession with the Earth rotation. And you might wonder what my evidence is for that peculiar statement, the palimpsest, that rotation lives on. My third artifact is the South Pole Telescope. The US maintains a scientific station at the South Rotation Pole, Antarctica. There are several experiments there, one of which is the South Pole Telescope in the dark sector at NSF Edmonton Scott South Pole Station. It studies the cosmic microwave background. I think that guy there in green, I have a sneaking suspicion he works at Fermilab. I think he's doing that because he's in awe of being underneath the rotation axis and he's staring straight up at the stationary point on the sky. But it's daytime, so you couldn't see the stars. What's the cosmic microwave background? Well, it looks like this. If you look in the optical and you look at a night sky and you map it all out, you get the map on the right, but only if you get rid of all the stars and try to ignore our galaxy as much as you can. And what you have left is a map of galaxies. If you look not in the optical, but at microwave, you get the map on the left, depending on how high resolution you have. That's not the highest resolution we have. It's fluctuations on a perfectly smooth background. Those are 10 to the -5 degree fluctuations on a perfect black body. So let me talk about black bodies for a bit, then we'll come back to what the meaning of those fluctuations are. Before Planck flew, which is a satellite, there was an American satellite called COBE in 1989. And one of its tasks was to measure the 3-degree microwave background to find out what temperature it really was. It's 2.725, and that's not nearly enough significant digits. It's now the most precisely measured black body known to us. There are error bars on that plot. If you blow them up 400 times, you start to see them. It is a nearly perfect black body if you take the whole sky at once and measure all the photons coming at once. You measure it in the microwave because that's where the particular black body peaks at about, looks like 150 gigahertz or 2 millimeters, thus microwave. The fluctuations I was talking about in the last slide are fluctuations in temperature. The black body shifts a little bit left and right, depending on where you are on the position on the sky. And those fluctuations are what will be important in a second. But first, I want to spend a couple minutes talking about what a black body is, because remember Plato, when he talked about the elements in his crazy work, he was talking about air, water, earth, and fire. But Timaeus is more clever than that. In Timaeus, Plato is actually saying, well, air means things that are gas, and water means things that are liquid, and earth means things that are solid. But fire meant fire to him. There was nothing he could describe. What was fire? He didn't have an explanation for it. He went on and worried about other things. But I can tell you what a black body is. I can tell you what fire is. So that's a candle. I thought about having a real candle tonight, but I didn't think I could photograph it well. So I just grabbed a video. That's a candle flame. I always wondered what a flame was when I was growing up. Eventually, I got to be in college. I was pretty sure it was hot gas, maybe even ionized gas. And that, in fact, is wrong. It is hot gas, but that's not what you're seeing. You can measure the spectrum of that, and that spectrum doesn't look like hot ionized gas. It's not made of lines. It's a broad spectrum. In fact, it's a black body spectrum. So isn't that just heated gas? So like, it is true that it's not. A guy named Michael Faraday in England in the late 1800s gave these Christmas lectures where he gave a wonderful description of what it really is. And in the end, it's soot. It's soot coming from the wick, being floated by the hot gas, but the soot is at 1500 degrees Kelvin, glowing as a black body. So when you see flame like that, you're seeing a black body. You know what it looks like. You know what a black body is. That's a black body. It has this very particular look to it. And we're all familiar with it. We just don't recognize it as a black body. I had to double check that candles were 1500 degrees Kelvin. That seems really hot to me because I have put my fingers in candles before. But that's, I am assured, is true. It looks about right if it was orangish light. From a candle to the universe again. But I have to tell you, we're talking about the very beginnings of the universe, the Big Bang. So we know almost nothing about the Big Bang, so I'm not going to talk about it. Like, we know almost nothing about the Big Bang. We're not even sure inflation happened, but we're pretty sure inflation happened. It solved so many problems. But what we think of as the Big Bang is the end of inflation, when it dumps a huge amount of energy into a pre-existing space-time. I mean, it's a mystery. We don't know what causes inflation. But if it happens, then it dumps this. I mean, we pretty much do understand how inflation ends, and it dumps an enormous amount of energy into the universe. All of a sudden, you have a hot, dense universe. And then over time, it cools. And we're going to spend some time talking about a hot, dense universe then cooling, because that too is physical cosmology. Why does it cool? Because the universe is expanding. Then I am going to show you another video because I like this video, because I'm going to use it to model the universe. Iron ball is our hero, by the way, not brick chunk. Let's see, 2000 K centigrade. So it's, I don't know, 2500 Kelvin. Iron ball, our hero, and a brick chunk. Yes, there's a black body. That's a technical description of a black body. If you have walls all hot and everything inside the oven is a perfect black body. Those things are not. They're not nearly hot enough. They're going to be putting in the oven to heat them up to make them become hot and therefore emit as black body. It'll take a while. We won't watch all of it. because frankly, you really want time to go by when you're heating something in the oven. There, that's black body. You recognize it? It looks just like flame, except for its black body. It's 2000 Kelvin iron on the left, the sphere, which is our hero. Why is the sphere our hero? Because Plato thinks the sphere is perfect, and therefore the world must be a sphere. And therefore, because it's perfect, not this messy, necessary matter, but the perfectness of the sphere. Right, so here he's going to take it out of the oven and start letting it cool. And that is what we're going to say is the end of inflation. And the universe has been heated. So we have our universe model, which is that. And what we're going to watch for a while now is it cooling, which is not the most interesting thing in the world. Sorry, wrong thing. Let's go with this one. Like I said, sometimes technology defeats the best intentions of scientists, engineers. Okay, the universe is still cooling. I mean, the universe is expanding ballistically. Once the inflation happens, it's essentially described by Newtonian physics, like throwing a rock up. It goes up, reaches the highest point as the energy dissipates, and then falls back down. As we understand the universe up until about 5 billion years ago, it was in that state where it was just going to reach the top of its trajectory after infinite time, a flat universe. And that's what that bulk of this plot is. There's the inflation on the left, there's something funny going on the right, but the bulk of it is just normal expansion, redshift, where galaxies are falling away from every other galaxy, and photons trying to get to us in those galaxies get redshifted. That's why the temperature is decreasing. There's both expansion going on, which dilutes the temperature, and there's also redshift going on. If you notice on the right, there is accelerated expansion. That's another mystery. As the universe cools, apparently that kicks in. What are these trying to show us? They're trying to show us photon travel distances. The photon just travels. By the way, did you see the universe leaked out? I'll get to what that is in our model. But the universe is now cool and it's over with. So photons travel. It's just the distance they travel in a second or a year. And it would just be c over c times dz, except that the universe is expanding. And the universe expanding makes the photon travel more or less, depending on the curvature of space. So this is the very beginning. And what do I want to tell you about this? This is diagram from 2012. You can watch how these things evolve over time as people change how they want to think about it. This one shows inflation more correctly than everybody else. These other diagrams I've been showing you. It shows you that inflation is over with very quickly. At 10 to the minus 32 seconds is over with. And the universe is 10 billion years old or so. And so you must use logarithmic time to understand what's going on in the matter in the universe as the universe cools down from the inflationary deposition of huge amounts of energy. Again, one of the great mysteries is what produces inflation. We just don't understand. We have like models, but we don't have anything that makes inflation really work. And this is what I was trying to get to. This is a thermal history of space-time. And this is a physicist view of it. It came from Fermilab in, 1984, when they used to draw things. But the way to think about this is that iron ball cooling, as it cools, various things happen. Around 10 to minus 30, inflation ends. around 10 to the minus 28, another great mystery happens. The annihilation of matter and antimatter. It's really the precursors. Matter doesn't quite exist yet. It's way too dense for that. But whatever happens, it produces way more matter than antimatter. So the current universe is only made of matter. That's called baryogenesis. We have some ideas for it, but we don't understand it. Around 10 to the minus 12th, the electroweak phase transition happens. That's where the photon decouples from the W and Z bosons. Above that temperature, they're essentially the same force. Below that, symmetry is broken and they're different forces. Electroweak phase transition might be able to be seen in gravitational wave backgrounds by LISA, which will fly in 10, 20 years. At 10 to the minus 5, it's the quantum chromodynamics phase transition. That's where quarks come into existence. Before, it's too hot for even quarks to exist. At about 1 second, we're finding again in human timescales, at 1 second, the universe is no longer opaque to neutrinos. It's no longer as dense as a neutron star in the center of a supernovae. At around 1 minute, protons form and neutrons. And soon after that, you start getting helium nuclei and lithium nuclei. It's called nucleosynthesis, and it works very well. You can predict the abundances of hydrogen, helium, and lithium very, very well. But they're totally ionized. The electrons are not attached to the nucleons yet. But around 300,000 years after the Big Bang, after inflation, really, the universe is cooled enough that protons capture electrons, hydrogen, neutral hydrogen forms, and the universe becomes transparent to light. And in my simple model of the iron ball, it winked out when it became transparent to light. When it becomes transparent to light, you can look back and see what it looked like back where it was opaque to light. And that's the cosmic microwave background. The moment when the universe became transparent to light, photons free stream from the cosmic microwave background to us. And the fluctuations in that could grow by the influence of gravity. The gas could form in deep, cold dark matter wells and form the first stars, the first galaxies, later elder stars, and later planet Earth. And around 5 gigayears, it's basically the same time the sun formed, the universe somehow became cold enough that acceleration again kicked in. And that's the third mystery. We really don't know anything about what dark energy is, what causes this cosmic acceleration. Aristotle again, for what is oldest is most honorable. You could say I took that out of context, but if you read Aristotle, he doesn't really have context. He's very murky. I will say that the oldest is most honorable is the status of the cosmic microwave background in modern cosmology. It's where we learn most things about cosmology. But it's not the only thing. My fourth artifact is Fermilab and CERN. This is Fermilab, where we study the standard model of physics, which could be thought of as the higher and higher energies is earlier and earlier back in the universe. So Fermilab and CERN are like time machines. Let's understand what was going on in the universe as it cooled. That's how we study the matter content.
Jim?
But there's also...
Yeah, I actually have my own question, so I'm gonna just kind of interlude.
Sure,
intrude
please.
at this point. So is it correct to say that all matter is considered black body, since basically all atoms are in motion and stuff, right? Because temperature is just a reflection of motion. Or am I understanding one thing wrong?
I would
Or
say
is there a
you understood
temperature where it
completely.
becomes non-black body?
You understood completely up until the point where the universe became transparent to light. And then it stopped being a black body. Matter in the universe stopped emitting black body light.
I see. Okay, nice.
I mean, stars formed, the sun's a black body, it's 5,000 K, 5,500 K. You look at it and you can see that very particular black body look to it. Don't look at the sun. So pockets of the universe became black bodies, but the universe itself and all the matter in it stopped being black body around recombination. I hope that helped.
Yeah, thank you.
So this is the Planck telescope, my last artifact. The European Space Agency put it up in 2007, a long time ago now, 13 years. It did the definitive measurements of large scale cosmic ray background measurements. It really nailed the measurements. We're going to start paying attention to what those measurements are now. Because they're both of these. That map I showed you earlier is the map of temperature fluctuations on the sky measured by Planck and the scientists who were in the Planck collaboration. Those fluctuations from red to blue are 10 to the minus 5 in degrees in Kelvin. I mean, remember, black body is 3 degrees Kelvin. They're just tiny, tiny temperature fluctuations, but they're well measured. You can see by that map. And again, 2018 map had a higher resolution than even this map. But if you take that map and take the Fourier transform of it and look at the power spectrum of the fluctuations, you get that plot I'm showing there. And I think I can do this. The red dots are data, and the blue is a theoretical line through it. So there's a couple things to take away from this. The data is great, but there's also a giant signal to be had. I mean, there are 7 peaks in that diagram. The first one is obvious. The next 2 are about the same height, fine. Then there's 3 and 4, they're pretty obvious. Then 5, and then 6, and maybe 7. There's probably more. The SPT is studying at scales less than a tenth of a degree in a region they call the damping tail. But that signal is what gives measuring the CMB and trying to model how the fluctuation came to existence so much power. The dotted line shows where you run out of sky. There's only one sky to be had over the whole sky, and the statistical limitations are large. It's called cosmic variance. There's interesting things going on there, but we can never really tell what's happening because we only have one universe. This is, again, a first principles thing, which is what this whole talk is obsessing about. Because from first principles, we truly understand things, said Aristotle and every physicist in the last 2,000 years, in the Western tradition at least, but also just the physical tradition. That first peak is the sound speed horizon. So horizon is as far as you can see before something stops you from seeing. The sound horizon is how far a sound wave, acoustic wave, a pressure wave can travel in that dense plasma of the early universe until recombination stops sound waves from traveling, because radiation decouples and then the matter behaves freely. So recombination is that special moment. We can calculate that sound horizon first principles if we know the cosmology, but that's why we measure the cosmology. And we can clearly measure the angular size really well of those fluctuations. That first peak is around a degree, and we know where it is exquisitely well. And it turns out that if you do the modeling, the location of the first peak tells you that the universe is flat. The amplitude of the first peak tells you that normal matter, like the rock I'm holding in my hand, is not negligible. The ratio of the first, second, and third peaks tells you the amount of all matter, mostly dark matter in the universe. And the ratio of the first, second, and fourth peaks tells you the amount of normal matter in the universe. It's astounding how well this works. Where by astounding, I mean that there's our 7 peaks again. If you look at the first peak, it's tall, that is indication that there's actually significant amounts of baryons, where significant means 4%. But look at the second and third peak, they're about the same amplitude. That's strange, but that has something to do with the ratio of dark matter to normal matter. And there are relations like that that you can think of. What they did in the lower left was to vary single cosmological parameters to give you a flavor of the idea. So the upper left is omega normal matter baryons. And look at the peak go up and down if you increase baryons. And the second on the left is curvature. The universe is flat or not flat. Well, you move the peak around, it moves really dramatically. We know it's very close to being flat. And then the upper right is how much dark matter there is. And the position of the first peak moves and its amplitude relative to the second peak changes. So what we do is we fit a 6-parameter model to this. That's what in the table, the first 6 parameters. I can do this, but these parameters aren't terribly interesting. They're the baryon content, the fractional baryon content, the fractional cold dark matter content, the size of the last scattering angle, reionization constant, the amplitude of fluctuations, and the scale length of fluctuations. But just because you only vary a 6-parameter model to fit the data doesn't mean you don't know other things. The model tells you all kinds of things, and that's what's below the bar. Interesting things like age of the universe, 13.8 billion years, plus or minus 20 million years. So exquisite data points like that. And I just want to say, this stuff is physically meaningful. I mean, it's just before recombination. What that plot's showing you, the animation, is trying to put in your head this physical model of you're in the early universe. It's a hot plasma. Light is not free to travel. Light moving pushes matter around, let's call it gas around. But there could be a local fluctuation of dark matter, which is the black line. And it tries to pull things towards it because gravity. But if you're a neutrino or light, you move relativistically and you'll try to free stream away from that matter. But if you're light, you're going to drag gas along with it until recombination happens and the light starts becoming transparent. The matter becomes transparent to light and gas starts doing its own thing. It's massive enough to pull dark matter into it and form a secondary peak at about 130 megaparsecs. So the way to think about that is that if you know a big peak of matter, say a cluster of galaxies, then 120 megaparsecs away, there's a higher probability of finding matter, clumpy matter there. But it's from every single red spot you see on that CMB map. But because it's physical, and that gas really does get moved, you might think it shows up in the galaxies too, and it does. So that map on the right is the galaxy distribution. And you could imagine looking for the signal in the galaxy distribution, the same physical signal. And in fact, you do see that. The plot on the lower left is a power spectrum of the 3-dimensional galaxy positions on the sky measured by the BOSS survey, which is a descendantless longitudinal sky survey. And you see that same multiple peak that you did in the CMB. I meant to say this to you. I really want to say this to you. Let me go back. Because for as all as flaky as Plato is, that peak is a fundamental frequency of sound at the horizon with recombination. And these other peaks are harmonics based on that sound. It's literally what's going on. It's exactly that. You can model it with a string and it works. So you can see these harmonics. You can see the peak and the harmonics in the galaxy distribution. And you can measure the height of this peak, I mean, the position of this peak on the sky in degrees as a function of redshift. And we've done that in several places locally. And we've done it, what's shown on here is 4 experiments that already run: the green, the red, the yellow, and the blue. But there's an experiment running now called DESI that's going to do the gray and maybe the black. And it's just going to measure this pattern in the galaxy distribution at all redshifts from 0 to 2. It's fabulous. And it's a direct measurement. Like that equation on the right-hand side, we know what our sound is. So we could just say that what we're measuring in the galaxy distribution is the sound speed at the sound horizon at the CMB seen at different redshifts and therefore different angular sizes. But the angular size you see has to do with the distance, and the distance has to do with the cosmology. And so you're measuring the cosmology directly from first principles. So I'm back to this. Physical cosmology is the matter, the standard model of physics, the matter content in the universe, which defines the way that photons travel, which is usually what I mean by saying about cosmology. I want to know how long it takes a light photon to travel the distance from an object to me. But that's really space curvature, that's gravity, that's general relativity. And always in general relativity, curvature tells matter how to move, and the matter tells space-time how to curve. And then back to Aristotle from 330 BC. For we think we know a thing, we know its first principles and origins and elements. What I've taken you through is learning about the cosmic microwave background, the fluctuations that showed up both in the cosmic microwave background and later in the galaxy distribution of all things, and relating these two patterns on the CMB and in the galaxy distribution is what cosmology in the 2020s is all about in a much more detailed and complex fashion that I shared with you tonight. But at its heart, it's measuring things from first principles.
Okay, Jim, I might jump in again with some of my own questions.
Sure.
I'm full of them. First of all, do you think the JWST data is going to dramatically change the WMAP CMB image, or just slightly?
Let me answer that by looking at this plot. So you see on the left is that starlight thing. That's supposed to be the Big Bang. Then you see the green was the cosmic ray background. And then you see darkness. And then you see glowing white. And then things that look like stars and like galaxies. And that's really what it is showing, what this graphic is meant to represent. What we can do these days is get the redshift up to about 5, maybe 6, which is basically where these galaxies are on the right-hand side. But we know from those galaxies, we know that they have lots of chemicals in them. Even these things that, they're 1 billion years old, there's not much time. Stars live longer than 1 billion years. So how did they get the elements? And the answer is, well, the very first stars have been super hydrogen and helium rich, but basically nothing else, no carbon, nitrogen, oxygen. So they must have lived fast, died young, and blown up spectacularly and spread carbon, nitrogen, oxygen through the gas that form the second generation of stars, which makes up the galaxies that we know. And JWST is going to look back at those first stars, watch them explode, and watch how the galaxies formed around them. So it's really telling us about, it's really going to be a really powerful engine for learning about how galaxies formed. It's not really a cosmology machine in that sense. It's not really looking at space-time curvature. It's not looking at how matter forms, but it really is answering that super fascinating question of, well, how did our galaxy form? And how did the stars in our galaxy get all its chemical elements?
Okay, and my again, kind of serving myself here with these questions, but when we get better at measuring gravity waves, do you think we will be able to pick up a signal similar to the CMB, but for gravity?
Yeah, I do. So let me tell you the story about LISA. It's a European mission, but the Americans want to join it because it's so cool. It's 3 satellites, probably at L2 where JWST is. They're about, I don't know, 3 kilometers apart or so. They shine lasers at each other and they form a laser ruler just like LIGO does. But they do it in space where there's no vibrations, assuming they can do their station keeping well. It goes to much lower frequencies than LIGO does. LIGO stopped at low frequency because the Earth is shaking all the time. Tides matter. When you get down these low frequencies, you get this really likely chance of something, of hearing. So I use the metaphor hearing when I talk about gravity waves, because it's closest to sound in our ears. Hearing gravity waves, hearing the gravity waves from the electroweak phase transition with various parts of the universe. Remember, it's super dense, much denser than a neutron star. Various parts of the universe undergo the electroweak phase transition at different times, and expanding waves as electroweak phase transition expand outwards and collide in each other. And when the collisions cause gravitational waves, enormous gravitational waves. And LISA is thought to be able to hear them. It depends on details and models. The standard model doesn't really have the phase transition I'm describing, but every extension the standard model does. The electroweak phase transition is way before the cosmic wave background. If we can start measuring that, that's such close to fundamental physics that it's spectacular. It's a super fascinating opportunity.
Okay, at this time, I'm not seeing any other questions, Jim. So, were you? I didn't mean to interrupt. Were you finished with your presentation then?
I did actually finish.
Okay.
And I thought your questions were right on target, actually.
Okay. So, Jim, if you're ready, we'll put you back online. And thank you very much, Jim.
My pleasure.
Thank you. Good talk. Okay, I'm going to share my screen out again. Kathy, if you're on, we're now going to do our officer reports. You're on mute, Kathy, if you're...
Actually, if I can interject,
I got it.
Sorry, Kathy. I just saw that I got an email question for Jim. So maybe we could switch back briefly to him.
Sure.
So this is from Susan Wilson. She says, PSDs are usually computed in 2D, i.e. along a chosen line through an image. Where are the PSDs taken here in this CME data, or would it not matter if it's homogeneous? If I said that right.
I'm thinking I think this question refers to power spectrum. It is in fact a 2D power spectrum that you're looking at. The one nuance, it would be just like taking a 2D power spectrum of an image. It's the same math, except that on large scales, at least, the sky is curved and you have to handle Fourier modes that aren't quite Fourier modes, but Legendre polynomial modes. I think that's getting at her question. I mean, really, for small pieces of sky, really, you just run a 2D Fourier transform on it.
Okay, and I'm sorry again, Jim. I got one more question. I want to try to get him in while we have Jim still on here. This is from I'm not sure, NF Jerome, whoever that is. He says he has a question about LIGO's gravitational wave detector. Could difference in the time? Wait, excuse me. Try that again. Could difference in the travel time of the laser pulses down each leg be interpreted as a change in the relative rates of the passage of time in the two legs instead of a relative change in the length of the two legs?
I'll answer that, but let me answer the previous question. One more thing. It's flat. The sky is flat in the approximation we work on. So it's all the same distance. It's all flat. So it's easy. For this question, sure, but you can't, when you're talking about gravity waves or even gravity, you can't, it's not Newtonian. So we know that. And so you can't separate time from space. It doesn't work that way. So what they do is they have those characteristic L shape to the laser interferometers, two arms. And partly that's because they're trying to cancel noise. So a real signal has to be seen in both arms. But it's also true that gravity waves, in particular gravity waves from a massive two-body orbiting system, have very particular pattern. I showed you a cosine. I hid the details that you actually have a plus polarization and a minus polarization. And the plus polarization would give you a signal in both arms, and the minus polarization would give you no signal in either arms. And even worse, even better, the orientation of the arms relative to the position on the sky gives you information because of the polarization of the gravitational waves. So we know they're not scalar fluctuations like a time variable because those patterns hold. The gravitational wave pattern is actually really cool. Like it's just sort of, and it's very simple because it's those two masses orbiting each other. Imagine you're looking down on them from top and you see the two masses spinning around each other at all times. So you get all the mass at all times. But if you're looking in the equatorial plane, sometimes the two masses are on the sky, so you see two masses. Sometimes they're aligned along a line of sight and only see one mass. And so sometimes you get less gravitational waves because they're aligned along the line of sight. It's a different talk. I could give that to you, but it's a different talk.
Okay, thanks, Jim.